How you guys doing today? Doing well? Here's the thing. So I'll try my best to finish up the chapter 15, or maybe just a little bit left over after today's lecture, and we'll finish up on Wednesday. But my plan is here. I want to do review session 3 times this time. So this Wednesday and Friday and Monday, because we have an exam next Wednesday and Thursday, right? No, next Wednesday and Friday. So we still have, after this, we still have 3 lectures, Wednesday, Friday, Monday, right? I'm gonna do the 3 full lecture time for review. So from this Wednesday, I'm gonna bring the actual problem, and we're gonna do problem solving together, Wednesday and Friday and Monday. So you'll definitely have a very good idea what type of question you'll see on the exam. No doubt about it. So if you can come in the lecture, because in different part we're limiting space here, you can go watch the YouTube channel too. So that'll be very good study guide for exam. So 3 times. So there should be, I think, hopefully enough time for us to have some good idea what the exam will be like. Okay? So anyway, so let's try to finish the chapter 15, hopefully today. But I'm not gonna hurry though. Okay? So just anyway, so we talked about the benzene over here. So we talked about the benzene, and this is very stable. This is what we talked about, very stable. Stability of the benzene here. They also, we looked at the bond length between those all the carbons in the benzene was about 179 picometer. Okay, so that means they're all well conjugated. So usually the single bond is about 154 picometer. The double bond is about 134. So this will show you all around. Like this is double bond, single bond here. But are also very similar and same bond lengths all around in this benzene, which is about very short bond lengths than a single bond, and very close to the length of the bond, carbon-carbon double bond over here. So that makes very stable, and we want to find out what's going on with this benzene structure over here. Okay? So we'll try to look at this in the energy diagram first. But once again, you don't have to memorize this one. This is only for your understanding. So obviously you don't have to memorize this one. Okay? But if you just listen to me once carefully, you have a better idea why is it happening in this way. Showing very stable form of the aromatic ring, like benzene. Okay, so you have a 6 p orbital can be conjugate in this benzene ring. So you have 6 pi electrons. Can be used for just the molecular orbital theory and the bonding and anti-bonding. So there will be 2. Okay, this is anti-bonding over here. Okay, so the best one, obviously, if you think about the lowest possible energy status you can think of, will be this one. So for this one, so we don't have enough space. I'll try to erase it, redraw it. So please follow with me very carefully. So if you draw this one, you have this one, right? Okay. So obviously, if you have all the same bonding structure, this will be the best one, right? They don't have no anti-bonding. There will be no nodes all around. It has very good bonding property there, because they are heading in the same part of plus and minus. This is very wave-like constructive interference there. So that makes all heading in the same way. So all making bonding here. Okay. This will be the one best scenario you can have, which is the lowest possible form. So we're gonna fill those two, the bottom two. Okay. So what might be the second best one? Okay. So there are two scenarios. Okay, there are two scenarios. So we done with this one, right? The second best scenario is this one. So either you can do here, here, those three, okay? But here, it's not, okay? So they are three p orbitals are conjugate on the each side. There is only one node crossing whole this ring structure. So this is not the linear anymore, it's a ring. So we have a somewhat node-like plane going across that one center of the ring structure, benzene ring. So this is what we call, so do you guys remember we used the node for the diene pi p orbital? But this is a node, but it's like a giant plane. So we call this nodal plane. Nodal plane. So one giant plane that we cannot find the electron crossing right into the center of the benzene. So that has only one. Those two only have one. Nodal plane. So obviously less numbers of nodal plane is better for bonding. Or if it's more, it's not good for the bonding. Because this is where you can find the no electrons, which is worse, not good for the bonding. So this is the second best one. So we only have one node. There's a one tricky one. I'm gonna tell you that is this one. So they are bonding on each side, but your nodal plane actually not at this time. It didn't go through between the carbons. It right into the center of those two carbons here. So there's only four orbitals there, because this is where you cannot find the electron. You cannot have an orbital here. But either you have a nodal plane going between or through. This is two second best scenario. Because you're only going to have, either case, you're going to have only one nodal plane. Make sense, right? Okay. So the in that case, you find the best scenario. Second best one is filled in here, and then this is kind of makes this benzene ring very special, because you have all 6 p orbital pi electrons are filled in the bonding energy status, which is a sign. So this is good. So this is not, we didn't fill. This is I'll say very briefly. This is the case you had 2, like this. So they have a 1. So this is nodal plane between, but also the one cross the 2 carbons in here. So in this case, you have what? In these two, as 2 nodal plane. Okay. And then the other one, so like I said, there's another one here, right? Another one looks like this. So it doesn't go through the carbons, but beside. Okay? So those 2 nodal plane, we'll separate them in the bonding status. So it'll be very anti-bonding, these 2. This is the second worst one. Okay? Makes sense, right? Okay. But the good thing is they can always fill the 6 in the bottom 3, which is the best, the only one best scenario and 2 second best scenario. That's good enough. So they don't have to go up to there. That makes this bond very strong. It's very stable. And the worst scenario will be what? They're all heading the other way to each other, the neighboring p orbital, right? Like this. So they're all just separated. So there'll be three nodal points, the worst scenario. Okay. So that kind of explains why we have this aromatic ring. The benzene ring is very stable, very unique, by just looking at the energy diagram. Okay. Can I move on? So you don't have to know this for exam. Only thing you have to know is why the benzene ring is so special than any other aromatic compound. So you don't have to memorize for this one for the exam, but please remember this. I'm gonna use this one very soon, right now, okay? So you remember this one. You don't have to memorize, but just try to remember. The reason why we try to keep this in your mind, you don't have to memorize, I'll tell you why. There was one German physicist who invented a certain rule for us to measure aromaticity of the compounds. We call this, his name is I think Erich Hackel, but it's obviously I don't know his German, I'm not sure how to pronounce this one, but it's a Hackel's rule, which we put it at 4n plus 2. 4n plus 2. So n could be any number, is integer including 0. 0, 1, 2, 3, and keep going. Okay? So if you look at the benzene ring, because of the good 3 aromatic ring structure. Oops. Do you guys remember the chair conformation of the cyclohexane? Do you guys remember this in Orgo 1? So if you look at the cyclohexane in the side view, it actually looks like this because it's a chair. You guys remember this, right? We kind of flipping the chair. Because of the aromaticity in this benzene ring, it's actually flat. It's actually planar. We call this is a planar. Because they're all so stable and very short in the bond lengths. They kind of held them very well together and very good stable. So they're in a very plane. They're all carbons in the same plane. That's what it means. And it gives some special property. We name it aromaticity. And to have this aromaticity in the compound, cyclic compound, you should follow Hackel's rule, which is 4n plus 2. N is including 0 is all integers you can put into n. Okay. So for example, if I give you cyclobutadiene, so cyclo means it's a ring structure, right? And buta means there'll be 4 carbons in the ring, right? So then 4 carbons in the ring. Just ring it. But you have a diene, right? So it will be 2 double bonds over there. Okay, there'll be 2 bonds over there. So if you have a cyclobutadiene over here, this is the 4n plus 2 is numbers of pi electrons. So if you count the numbers of pi electrons in here, there'll be 4. There'll be 1, 2, 3, and 4. Okay. So if you look at this one here, you can have 4 pi electrons. So based on Hackel's rule here, 4n plus 2, and if n is 0, the minimum that you can have for the pi electrons to be aromatic compound is 2. And the next biggest one is the 4 times 1. N is 1 plus 2, so it'll be 6. So either they can have a 2 or 6 pi electron in the ring structure that can be aromatic compound. But this one has, like I said, one for each p orbital, so they can be conjugate a certain way. But there are 4, not 2 or not 6. So this is the not. So cyclobutadiene is not aromatic. And we actually call this anti-aromatic. Because they not following the Hawkes rule to be aromatic, so it's not aromatic compound, but also it's in the same plane. So this is quite unstable. So if you do I speak too fast? It's okay. No. So if that is the case, this is not aromatic, anti-aromatic, meaning it's actually quite reactive. It's not stable, meaning it's quite reactive, meaning we'll do some chemical reaction. So whenever you do this, here in the negative 78 Celsius degree, they will do DLs. We learned this one, right? All the reaction. So they dimerize. So they make cyclobutadiene dimers. They look like this. Okay. So which actually means that it is indeed not so stable. So that's why they want to do dimerization at low temperature, which also means it doesn't have aromaticity much. It's not so stable. So if you actually look at this one, it actually looks like this. Either way, cis and trans. Yeah, go ahead.
Can you do another example of the rule?
Yeah, the other example, right? What was that again?
Yeah.
Hawkes rule, yeah, once more, right?
Yes.
Yeah. So the Hawkes rule is 4n plus 2 rule. This means if you have this many numbers of pi electron, that means this compound this cyclic compound will become aromatic, like the benzene ring we just taught. So pi electron is meaning in any electron can be used for double bond or triple bond. And also electrons in p orbital can be conjugate with other p orbital electrons. So either way, so technically if you just count the electron in the double bond or triple bond, that'll be most of the time you'll be good. Few exceptions we're gonna talk today is the lone pair, but we'll get this. Okay? But if you have following this rule here, minimum the number you can have is 2, because like I said before, you can put 0 in n over here. So 4 times 0 is 0 plus 2. So minimum number you can have for aromaticity is 2 pi electrons. So this is not in your textbook, but the one example would be looks like this one. So you have 2 electrons in the p can be conjugate, right? And then it has a 2 pi electron because this is a cation. So this is carbocation. They don't have any electron p. So its p orbital on this carbon is bacon. So it has a 2 pi electron, right? And this compound can be also aromatic, okay? Because there's 2 pi electrons. This is not in your textbook, so you don't have to know, but that's also possible. But most importantly, what might be the best one? What we talked before? Benzene. Because if you count this one over here, 1, 2, 3, 4, 5, 6. Okay? So that makes the 4 times 1, when n is 1, plus 2, makes 6 pi electrons. So this is also another good example of aromatic compounds. Makes sense, right? Does it make sense? We good? Oh, perfect. So let's take one more. Okay. Once again, we'll do this again in review anyway in the actual problem. But please let me know if you have any question. The question was very good. Okay. Any question? It's very good. Sleep. Oh, sorry. Okay. Okay. So can you guys actually name this one for me? This is a cyclic compound. So it's a cyclo, right? Cyclo. How many carbons in here? How many carbons? Cyclo. Oh, it's 8, right? Perfect. Octa. And then you have a 4 double bond now. It's 4 double bonds. So it'll be tetra. Because we put cyclobutadiene because we had a 2, so di N means 2 double bonds. But you have a ring cyclic compound that has 8, so it'll be octa means 8 carbons in the cyclo structure. But we put tetra because we have a 4 tetraene. Okay, so this is the cyclooctatetraene. Okay, so kind of makes sense, right? So we can say we have a 4 double bonds over here. So in this case, we just try to count the numbers of a pi electron again. Okay. Okay. Same here. Can you guys guess how many pi electrons are there? 8, right? 8. Perfect. Because we have a 1, 1, 1, 1, 1. So it'll be 8. So you have 8 pi electrons. Okay. So then also, so if you think about 4 times 0 plus 2 is 2. 4 times 1 plus 2 is 6. And 4 times 2, this is the third best, the highest, smallest number you can try. That's 10. So unfortunately, 8 doesn't go into any of 2 and 6 and 10. So this will not be aromatic. Makes sense, right? It's not aromatic. Here's the rule. You don't have to know. If this is a 4n numbers of a pi electron, we call this anti-aromatic. That's why we call that cyclobutadiene as anti-aromatic. For this one, you don't have to do it as anti-aromatic. You can just say it's not aromatic because it's not planar. So what it looks like. So when is that cyclic compound is planar and also 4n pi electrons are there, it's anti-aromatic. But if it's not aromatic, but this is not in planar. It actually looks like a tub. Like a tub-like structure. So you can just say it's not aromatic, but you don't have to say anti-aromatic even though it's 4n, which is 2n, 2 times 4 is 8, right? But you don't have to do it as anti because it's not planar. Okay? You can just say it's not aromatic because it doesn't follow 4n plus 2 to be aromatic compound. Okay. All right, so can I move on? It's pretty easy, right? Because it's 4n plus 2. That's pretty much it. And once again, you don't have to know about the anti-aromaticity. It's okay. Just if you do count the numbers of pi electron, if it's not 4n plus 2 numbers, you can say, oh, so it's not aromatic. If it is, it's aromatic. So let's talk about a little bit of a bit more complicated one, which we call this the aromatic ions. Okay? So not just for the neutral compound, we can have some ionic molecule that shows the aromaticity as well. So one good example is this one. Okay, so if you have this type of 1,3 cyclopentadiene, right? Pentadiene, right? Cyclo 1,3 pentadiene. See there, right? Okay, so you can treat it with some base. Okay, and then it'll be deprotonated. So you can have this carbon will have 1 lone pair. After this proton leave, with the base, and it looks like this. Okay. So this is a kind of tricky one because those lone pair will stay on the P. Okay. Because the other three. So obviously this is a negative charge. This is a carbanium. Okay. This is a carbanium. You see, there's a pair of electrons donated to the carbon when it left. Okay. So this one has more than 4. 1, 2, 3, 4, 5. So it's a negative charge. Okay. And there's 3 single bonds to the hydrogen and 2 other carbons over here, and 1 lone pair on the top on the carbon in p orbital. So in this case, you have this one here. So we're gonna call this the cyclo. It's a penta, right? Penta. We have 2 double bond, right? Penta, di, and but it has a ionic form because it's a negative charge here. So we'll have a dinyl YL anion because it's a negative charge. So we can call this cyclopentadienyl anion because it's become an ionic molecule by just having one more electron on this carbon that makes this one a negative charge. So but the point is when you look at the lone pair, it's located in the P. Okay, so in this case, this cyclopentadiene anion is also become aromatic. And you're saying, what do you mean? We only have 4 p orbitals, 4 pi electrons are here, but like I said, you have a lone pair on this carbon, but these 2 lone pairs are located in p orbital. So it can be also conjugate. So if you remember, there's 1, 2, 3, 4, 5, and 6. Okay. So that comes to this one. So it's a 6 now, not 4, because of the lone pair on this carbon. Okay. It's kind of tricky, isn't it? Right? So when it becomes ion, you can say it's some IYL anion because there's one negative charge. So we're gonna call this cyclopentadienyl anion. That the lone pair on this carbon, this negative charge, are located. There's 2 pi electrons located in P. That's why you can count those 2 as in your aromaticity rule, which will be 1, 2, 3, 4, 5, 6. So this will become aromatic. This is a 6, not 4, because of the lone pair. Okay. Can that make sense? Kind of makes sense? Okay, perfect. So if that makes sense, we can also look at the other case that is a cation. Okay, so you have 7 here, right? 7. Okay, and then you have this one, and then whenever you have this compound go through the bromines, okay, bromines, you can have a cation, which will happen here. So 1, 2, 3, 4, 5. Okay, so this carbon will be positive charged with only 1 hydrogen. So it was stolen by this bromine. Okay, and here. So whenever you do right, and then they cast to this one whole thing, and then they become here, right? So in this case, actually this is the reaction we found like a century ago, but that time we don't have a good technology to find out what happened, but we do know now. Here, so in this case, it's kind of a little bit vice versa we did for the cyclopentadiene anion. So this is what we call cyclo. So there'll be 7, right? 7 carbons. So it'll be hepta, and you have a 3. So it'll be triene. Okay. The cycloheptatriene, but this is now ion, right? So dianyl cation. Okay, so unlike the one we did before, this one actually has no electron at all on P because it's a positive charge. It lost the electron there, so that's why it's positive charge. So when you look at this P orbital in this carbon, it's vacant. It's nothing there, no electrons there. So you not count for any pi electron counting on that carbon, but those other 6 carbons. So there's a 7 carbons. Obviously, it's a cyclopentatriene cation. But because of this carbon is positive charge, they don't have anything in the p orbital. So you can count here for your pi electron counting. So it'll be 1, 2, 3, 4, 5, 6. So it still has 6 pi electrons. So this is also aromatic. So this is aromatic ion. So meaning there's the cyclopentadiene anion and cycloheptatriene cation are both aromatic. So they will be also delocalized. The electrons in the pi electron will be delocalized, and they show very good aromaticity. That's why these 2 ion molecules will become also very stable, like it does in the benzene ring. Okay? Because it also satisfies Hooker's rule, which is 4n plus 2. Okay? Makes sense, right? So if there is a positive charge, don't count that. Don't count that. If there's a lone pair, count it 2. That's all you need to know for counting the pi electrons and the compound. Can make sense, right? All right. So we're almost done. We're almost done. There are a couple more topics in the chapter 15, but this will be the last topic I want you to study for the exam 1. Okay? So this is what we call heterocycles. Cycles. Or you can say heterocyclic compound. Either way is okay. They're the same thing. So heterocyclic compound means that this benzene ring, you have only carbons in here, right? In the ring structure here, right? But what if you have other than carbon, like nitrogen over here? Okay. Okay. This is a pyridine. Okay. Pyridine. So this is a pyridine. It has the nitrogen instead of carbon in this position here with the lone pair over here. Okay. So this is also a good example of the aromatic compounds because you have so nitrogen also has the p orbital because if you look at the position of the nitrogen in the periodic table, you have the nitrogen is in the p block position right there, right? So you can count as 1, 2, 3, 4, 5, 6. Okay, so that will show you 6 pi electrons. Okay, so now you're saying, oh, what about this lone pair here? What do you do? So they have a lone pair because because it has a. What can I say? So do you see those double bond here? Double bond here, here and here and here. It's the combination of the sigma bond and the pi bonds, right? You know that? So pi bonds is the one that coming from the p orbital. But it has also 1, 2, 3, okay? The p orbital, and 4. This is the sp2 orbital, not p. So it's a hybrid orbitals. There's a sigma bond between these two, and this is the same thing. And p orbital is a separate and on the top. Does it make sense? So I will show you. Okay. So one more. It's okay. We can always do this on Wednesday again. So if you have this one over here, right? Okay. You have a lone pair here, but that is one part of your hybrid orbitals because let's think about there's one electron here and one electron here share, which is what? Sigma bond, which will be hybrid to be the same bond length, maybe not here, but initially has to be in the same. So this will be hybrid orbital, which we call sp2, because that makes 3. If it's 4, it's sp3. I'm sorry, sp2. If it was 4, it would be sp3. Because to make carbon to be same bond length on the 4 the other way, it had to have a 4 electron to be shared, which will be 1 from the s and 3 from the p orbital. So we call this sp3. But here nitrogen only do 1, 2, 3. 1, 2, 3. So say sp2. And there's another one on the top is p that is the only one that involved in this p orbital conjugation in this the aromaticity. Does it kind of make sense? Okay. So this is lone pair. You don't have to count because I know it's tricky. I totally understand because it will be even easier for you if you think there is the hydrogen bond but it's not actually because this is a number group 5. But what it does is those lone pair as another one of the three sp2 hybrid orbitals for initially for bond lengths. So the only one on the top of the P will be used for aromaticity, Hooke's rule, the pi electron counting. So it'll be 6. So this pyridine will be still aromatic because it's 6, not 8, 6. Because these two lone pair will be in sp2 orbital. Okay, so this is a bit tricky. If you look at the pyrrole compound, it is similar to this one, pyrrole, but this is what it looks like. Okay, so in this case, if you look at this one carefully, as you know, this is like this one, right? And then you have a 4, obviously, because there are 2 double bond here. And here, you count this lone pair on the nitrogen as in the P. Because you have a bond to hydrogen over here. You have so those are 3 hybrid orbitals or sp2 are over there already. So the lone pair doesn't have to be fit in that one of the hybrid orbitals, but on the P. Because it's a hydrogen over there. Does it make sense? So they'll use this nitrogen here. There'll be 3 sigma bond, single bond, has to be hybrid, which is sp2 because only 3, not 4. And those 2 remaining lone pair here has to be fit in the P then because it's leftover. So that's what they nitrogen didn't need to have for the hybridization. So these 2 will remain in the P. So it's actually not 4 or 5, but it's 6. 1, 2, 3, 4, 5, 6. It's kind of tricky to me. I understand. But we'll definitely do it more on the next time too. Okay. So let me give you just one more example, and we'll finish up on Wednesday, and then we'll do the review session for Wednesday. Okay. Because whenever we cover this again in review, hopefully we can have a more practical way to solve the problem. Okay. So another one is has a 2N, not just 1. So we call this pyrimidine. It has this one. Only thing difference here is they have a 2 sp2 orbitals. This one difference. So we still count this one as 1 for these 2 nitrogen as well, and other carbons as well. So it'll be 1, 2, 3, 4, 5, 6 over there. And there's just unlike the pyridine, it has 2 now. So it has a 2 lone pair located in the sp2, not p orbital. So this is not either 8 or 10, but just still 6. 1, 2, 3, 4, 5, 6. Okay. Same reason that it has only 2, so it has to be one lone pair as kind of behave like one of the 3 hybrid orbitals, which is sp2. So if we go this pyramid. Let's talk about this once again on Wednesday. I'll do this again Wednesday. So this is the last one that I want to study for the chapter 15. So it only takes about 5 or 10 minutes to cover this one on Wednesday, and I'm gonna spend any time after until the exam 1 will be the review session. So if you cannot attend the lecture, you can watch it on YouTube, but make sure you watch them because there'll be a lot of helpful sort of a study guide like a review session there 3 times. So you have enough time to work on the exam problems like practical session, okay?